Hello and welcome. My name is Serge Beauchamp and I work for Freescale Semiconductor. This talk was originally presented at EclipseCon 2011. Let's start with a historical perspective. Programs used to be single-threaded. Everything ran off a single thread. It was very simple, very clear to understand, program and debug. But obviously, user wanted more responsiveness, performance and efficiency. So the next step was to pepper the main thread with code that was pulling the event loop queue for events. This wasn't very efficient and actually turned out to be slower than the previous design, but was at least more responsive. The solution was to spawn off the task of different threads, so that the main thread can be dedicated to responding to user events, and the task would be independently executed. The next step was to execute those threads in parallel to be more efficient, and finally to slice up those tasks into independent subtasks that can be executed in parallel to take advantage of multi-core and multi-CPU hardware. Now, that looks great in theory, but how does it look in practice? If we take Eclipse, which isn't unique in this respect, but is a good example of how Java programs behave, we can gather performance statistics on multi-core hardware, in this case, a 6-core i7 CPU with 12 hardware threads with hyper-threading. We can see that starting Eclipse Workbench UI takes about 12% of the CPU. Note that those measurements are done on a Windows machine, which report CPU usage percentages as a fraction of 100% of all hyperthreads utilized. So if a program saturates a single thread or core only, it will only show about 8 or 9% CPU usage, as opposed to macOS 10 or Linux, which will report it as 100% CPU usage, and fully saturating the 12 hardware threads will report 1200% CPU usage. So starting up the Eclipse Workbench UI utilizes roughly a bit more than one single core. Running a JDT build with 300 projects never exceeds more than 10% CPU usage. Even though it spawns more than 3000 threads, almost all of them are extremely short-lived, and only a single thread consumes the CPU cycle. File search is a bit worse, and its performance will degrade exponentially with the number of search results, due to a bottleneck in the tree viewer displaying the search results. The search operation itself, though, is single-threaded and never uses more than 10% CPU usage. CDT indexing also never exceeds more than 10% CPU usage and uses a single thread. And finally, CDT build is the only task that utilizes more than a single core, and this is because it calls either make.exe as an external process, and which handles then the parallelization, or spawns off different processes for the compiler. In either case, it escapes Eclipse concurrency constraints by using external processes. Also to note is that those tasks are not I/O bound, since those statistics were gathered on a machine with 4 SSD RAID array setup, with more than 600 MB throughput and 125,000 I/O per second. The maximum throughput used by those tasks was about 2.5 MB per second. So where does it go wrong? If we go back to the diagram where we spawn those tasks in different threads, those tasks still access some data structure shared between threads, including the main thread. The lines we see now represent the other threads blocking while they acquire a synchronization primitive to protect data structure against concurrent access. When we run those tasks in parallel, it becomes quickly more complicated. Worse, those tasks are not the only ones being scheduled on independent threads. Almost any runnable can be scheduled to run in parallel in Eclipse, accessing almost any API, with very few exceptions such as SWT. The synchronization primitive lock ordering can become an extremely complex maze when those runnables are all executed in parallel. In Eclipse, simply starting up the Workbench UI and having project displayed in the workspace can cause more than 27,000 individual unique lock to be acquired in release, bringing me to my main topic of my talk. Deadlocks happen when synchronization primitives are acquired in an inconsistent order between different threads. The more locked they are in a program, the more likely deadlocks are too. Deadlocks are worse than crashes because the users might not recognize them as bugs right away and will waste time trying to figure out whether they are simply long-lasting operations or actual bugs. They rely on race conditions to occur, so they might very well pass unnoticed through the quality assurance process. They might not be reproducible on a developer's machine, so they can end up being the most expensive bug category, along with memory corruption. Here, I won't go into details about how exactly deadlock can happen, assuming everybody listening to this talk is familiar with this, but I want only to underline the terminology I will use. Lock A in working thread 1 is the precedent of lock B, because it needs to be held while lock B is tentatively acquired, and lock B is the follower of lock A, and vice versa on worker thread number 2. The more followers a given lock has, or in other words, the coarser granularity the lock is, the more likely it is to cause concurrency problems. Going back to Eclipse, with its 27,000 locks at startup, the single lock that has the most followers has over 12,000 followers. There are more than 118 locks that have more than 100 followers. There are generally 3 ways to solve an existing deadlock. The first way is to simply remove lock followers, or have a smaller lock granularity. The developer, by looking at the code, could conclude, for example, that lock A doesn't need to be held while lock B is acquired, so their dependency can be removed altogether. This can be done in the simple code by avoiding having a synchronized method and instead acquiring individual locks for the map and the listener list. We can realize too that the listener list lock can have very large follower count depending on the listeners being called while the lock is held. So we can simply hold the lock while duplicating the list, then iterating through the duplicated list for calling the listeners. Another way to resolve deadlock is to remove non-transitive follower chains. By this I mean that in this example, on thread number 1, lock A needs to be held while lock B is acquired, and lock B needs to be held while lock C is acquired. But it's not true that lock A needs to be held while lock C is acquired, so that the chain is non-transitive. The code acquiring lock B and lock C can be relocated on a smaller calling stack to avoid having the lock A as precedent, effectively eliminating the AC acquisition order from the global acquisition order list. One way that one could be tempted to accomplish this in Eclipse would be to use a UI job or the display.async.exec API. So to create a new runnable acquiring lock B and C and hoping that the runnable would be executed from the main event loop. Unfortunately, UI jobs runnable can be executed from totally random code paths. For example, if the original code path uses a sub-progress monitor, it can call the display.read and its dispatch API to check for user cancel events, and as a side effect, execute the runnable right away. Worse, this behavior is dependent on a race condition on the workspace runnables blocking on other threads acquiring conflicting scheduling rules. So it's very possible that the developer uses the UI job and verify that the runnable is executed where intended, only to be executed in the code path we try to avoid when the code is actually executed on the user's machine. A third way to solve deadlocks is to generally reduce concurrency. This can be done by acquiring more locks, for example acquiring lock A in thread number 2 in this example, or acquiring a third lock C in both threads. The Jobs API, although it was very good to address the issues for which it was designed, also leads developers into exacerbating concurrency problems. For instance, the Jobs API allows the user to set a single scheduling rule for the entire job, virtually guaranteeing that it will have a large follower count and a coarse log granularity. Jobs also automatically use a thread pool. That's great if you need a thread pool, but it can otherwise obfuscate the threading pattern. For instance, the user might experience a deadlock because when the runnable executes on his machine, it spawns off a new thread, while the same code executes on the developer's machine reusing an existing thread, ordering prediction very difficult. Another problem is that a job is associated with a single runnable. There is no API to schedule different runnables of the same job, which effectively promotes the proliferation of independent threads. The scheduling rule API also has some limitation. Because a job can only hold a single scheduling rule at any point in time, APIs are discouraged from using scheduling rules as the general mechanism to enforce a consistent lock acquisition pattern between locks. If multiple important APIs would be to require the usage of scheduling rules, as the core resource API does, calling multiple APIs in a single code path quickly become unmanageable. A typical motivation for using a jobs API is to avoid blocking the main thread. Because of this, a large number of independent threads are spawned. This is because we have a threading model in Eclipse where there's a single privileged thread, main thread, and there's a symmetric collection of independent threads. If Eclipse had a second privileged thread, namely a common thread, that random task can be scheduled in order to simply avoid blocking the main thread, the overall lock acquisition order would be greatly simplified. By scheduling short-lived and API-rich jobs on the common thread, and leaving long-lived and performance-critical jobs on independent threads, it becomes easier for performance-critical jobs to be parallelized, since they don't have to deal anymore with the unpredictable and very complex lock ordering pattern that short-lived tasks running on independent threads can cause. Now, this all looks fine in theory, but again, how does it work in practice? Going back to the 27,000 locks, here's a matrix with one square for each single one of those locks. When getting a deadlock report, we typically have information about 2 locks. We can try to use the techniques we just described to solve a deadlock, but the fact remains that we don't know anything about the other 26,998 locks in the program. We don't know how many are precedents and followers of those 2 locks. If we solve the deadlock by changing the lock order slightly, which is typical, we can very well cause another deadlock in a different code path without realizing it. We are completely blindfolded. So this is why we end up with getting poor hardware utilization percentages, because concurrency is very hard to manage in large programs. Here's where the Deadlock Preventer, a free tool released by Freescale Semiconductor under the EPL on GitHub, can help. Using that tool enables us to get information on those 27,000 locks. We can look at a random lock and get to know which ones are its followers and precedents, along with their stack traces and thread IDs in which the relation was created. Even better, without having to rely on a race condition, the tool will automatically report inconsistent lock acquisition and display a dialog. We can also stop in the debugger and investigate the lock right away before it hits the customers. We can abandon the old cycle where we'd get the deadlock reported with some lock, being able to reproduce it and debug it, then attempt to fix and hope that the fix didn't cause any further deadlocks, to a cycle where we can actually detect the potential deadlock before it happens, debug it, fix it, and validate that the fix didn't cause another deadlock in another code path. The tool can also be used as part of an automated test process, so it can overview all lock acquisition order with a large code coverage to detect a maximum amount of potential deadlocks. Here's how the Deadlock Preventer view looks like. The developer can select an existing launch configuration for the menu and click Debug to launch the program with the Deadlock Preventer. The developer can double-click the program in the Conflicts tab and get the complete list of all the locks acquired up to that point in the program, along with their followers and precedents. The list can be used right away to figure out where to start improving the concurrency of a program by looking into the best candidate for refactoring the code and removing unnecessary followers. By using the Deadlock Preventer, developers can significantly reduce the cost of managing concurrency to better leverage multi-core hardware. The Deadlock Preventer is open for contributors. The UI is still very rudimentary. We could imagine a much better data mining interface to display the lock's information, filtered by package and plugins and so on. The lock follower count could also be used in code metric tools. Finally, to learn more about the Deadlock Preventer, please see the blog sergebeauchamp.blogspot.com. Thank you.